In the previous lecture, we discussed one unifying idea in this course. As we've seen, this course covers so much territory that it's very important to be clear about the ways in which we can construct a coherent account across all these disciplines. And the idea we looked at in the last lecture was the idea that to fully understand the past on the scales of big history, we need to explore it at multiple scales. And we saw that each scale can illuminate the others. We also saw that each scale can affect how we understand other scales. For example, I ended with the idea that I said depressed many of my students, and indeed it did, which is that the colossal scales of big history seem to make humans and human history utterly insignificant. Now, as we'll see in this lecture, that is really not the end of the story. So now what I want to look at is a second unifying idea of big history. Because we face another fundamental difficulty, not just the difficulty of scales, but the problem of coherence. What thematic coherence can you possibly find across all these scales and all these disciplines? If you tell a story that begins with cosmology, includes geology, then biology and human history, isn't it bound to be just a ragbag of completely separate stories? After all, in universities, each of these stories is told in quite separate departments, and most of the time, very little attempt is made to link them, to string them together. Is there anything that all these scales and all these different disciplines share? Well, what I want to argue in this lecture is that there is a central idea, and that idea is the idea of increasing complexity. And we've seen already that the idea of increasing complexity provides a sort of structural framework for this course. It's an idea that's emerging in the writings of a number of scholars who are thinking about the implications of big history, of unified accounts of the past. And what I'll do is that this idea links all the different parts of our story in very powerful ways. Furthermore, I'll argue that it shows how each part of the story can illuminate and deepen our understanding of the others. Just as we saw that understanding different scales can help us understand more familiar scales in new ways. Okay, so our theme is complexity. Let's begin by asking, what do we mean by complexity? What is complexity? Now, we all have an intuitive idea of the difference between simple and complex things, and that intuitive sense of complexity will take us quite a way. There is an incredibly rich body of mathematical, sociological, and biological theory on complexity. I'm really not going to go too far into the nuances, and we don't really need them. Some fairly basic ideas about complexity will take us a long way for this course. So here is an attempt to pin down some of the properties of complex things. Here's the first thing. Complex things like stars or planets or you and me consist of diverse components bound into larger structures. And I need to add that those structures are patterned in very precise ways. So that's the first thing. You take a lot of components and you put them together in a particular structure. Now here's a second, slightly less obvious feature of complex things. These structures that bring together diverse components display distinctive emergent properties. Now the phrase emergent properties I'm using in a slightly technical sense. I mean features that are not present in the components from which they're constructed, but appear only when those components are assembled in specific ways. Now, the idea of emergence is going to be immensely important in this course, so I'm going to take a bit of time to try and clarify it. Here's a very simple illustration. You could study the properties of hydrogen and the properties of oxygen as long as you liked, without being able to predict properties of water, which is what you get when you combine two hydrogen atoms and an oxygen atom in a very specific way. The properties of water are emergent properties. They exist not intrinsically in the components, but because of the way those components are arranged. They arise from a particular arrangement of those atoms. Rearrange them differently, and you may get different properties. The idea of emergence, it turns out, is actually a very old one. And there's a lovely illustration of this in a Buddhist sutra, which is known as the Questions of Milinda. And I want to go back about 2,200 years to the Questions of Milinda to explore the idea of emergence and to try and capture the magical quality of emergence. What's magical about emergence is properties appear that seem not to reside in anything in particular. They just suddenly appear when you rearrange those things in a particular way. They appear not to be present, then suddenly they appear. They appear only in a particular arrangement. Okay, so the Questions of Milinda. Milinda is the name in this Buddhist sutra for a Greco-Bactrian ruler who ruled a kingdom, an empire that stretched from Central Asia to Kashmir in about the 2nd century BCE. He's debating with a Buddhist monk, Nagasena. And what they're debating is the Buddhist idea of the self. The Buddha famously argued that in some sense the self doesn't really exist. We all have a very strong sense of the self, but the Buddha argued in some sense it's illusory, and this is what they're debating. The Emperor Milinda, as he's described in the sutra, says to Nagasena that the self is real. Nagasena says to the emperor, "How did you come to this meeting?" Milinda says, "In a chariot." Nagasena asks, "Then please explain to me what a chariot is. Is the pole the chariot?" "No, reverend sir," says the emperor. "Is then the axle the chariot?" "No, reverend sir." "Is it then the wheels, or the framework, or the flagstaff, or the yoke, or the reins, or the goad stick?" "No, reverend sir." And as with all the Buddhist sutras, this goes on and on and on for pages, to and fro. Then, and I'll skip all of that, then eventually Nagasena says, "Then, is this chariot outside the combination of pole, axle, wheels, framework, flagstaff, yoke, reins, and goad?" "No, reverend sir." Then, says Nagasena, "Ask as I may, I can discover no chariot at all. Just a mere sound is this chariot." And at this point he claims victory. And he says, "It is just so with me." In other words, with the self. Independence on the 32 parts of the body and the 5 skandhas, these are simply Buddhist technical terms for the components of the self. There takes place this denomination Nagasena, this designation, this conceptual term. In short, what he's saying is that the self, like the chariot, doesn't exist in any of the bits and pieces from which it's made. It exists, or rather it emerges, as a property when you assemble those things in a certain way. And this is characteristic of emergent properties in general. When assembled into larger structures, new things appear. The sociologist Durkheim, one of the founders of modern sociology, was also acutely aware of emergence, and it was very important to establish the credentials of sociology as a discipline, because what Durkheim tried to establish was that in society there are properties that do not reside in individuals. Society has emergent properties of its own. And here's how Emile Durkheim described what I'm calling emergence. Whenever any elements combine, and, by the fact of their combination, produce new phenomena, it is evident that these phenomena are not given in the elements, but in the totality formed by their union. And then he goes on to talk about life as an emergent property. The living cell, he writes, and he's writing the 19th century, remember, contains nothing but mineral particles, just as society contains nothing but individuals. It is obviously impossible, however, for the phenomena characteristic of life to exist in the atoms of hydrogen, oxygen, carbon, and nitrogen. For how could the properties of life exist within inanimate elements? Life is in the whole, not in the parts. So I've spent some time with this property of emergence. It's absolutely crucial, this magical appearance of new qualities when you get a new level of complexity. So that's the second property of complex things, emergence. Now the third property. This is much simpler. Complex entities have a certain stability. Now, this is, in a sense, stating the obvious. If they didn't have any stability, we simply wouldn't notice them. They'd pop up, they'd vanish, we wouldn't see them. So they have to be stable to a certain extent. Atoms or stars survive for billions of years. Butterflies survive for just a few days. So they survive long enough to be interesting. But the stability is never absolute. Eventually, they all break down. And in the case of living organisms, we call this breakdown death. Now, a fourth property that's less immediately obvious. And this is that to maintain complex things, you need energy flows to bind simple components into more complex structures. Without these flows, the structures simply break down. If you want to try this experimentally, try not eating for a year. Very simple. Your structure depends on energy flows. So, we study complex things, partly because we are complex. But there are also good biological reasons for this. To survive, we must be extremely good at detecting complex things in our surroundings, such as tigers or tax inspectors. We need to be good at detecting complexity. We need to be complexity detectors. And that is why this course will focus more on complex things, such as stars, than on the simple things, such as empty space, that take up most of the universe. After all, if I were to try and make this a sort of equal time course, we'd spend most of our time talking about empty space, and I don't think that would be very exciting. Okay, now the next point about complexity. Though one of my heroes, Stephen Jay Gould, has disputed this claim, there are powerful reasons for thinking that over 13 billion years, the upper level of complexity in the universe has increased. Now, how can we demonstrate this? Well, intuitively, it seems pretty clear. The early universe, we'll see, was very simple. It consisted of hydrogen, helium, and energy, not much else. Now, 13 billion years later, there are lots of complex things, such as planets and pythons and people. So that's the intuitive demonstration of what I mean. But there may also be more rigorous ways of trying to say this. The astronomer Eric Chaisson has been teaching an astronomer's version of big history in Boston for at least 20 years. And he has argued that if it takes energy to create and maintain complex things, that ought to mean that that it takes more energy to make more complex things. Now, what this means, roughly speaking, is that if he's right, we ought to be able to roughly measure levels of complexity by measuring energy flows. And this is an experiment that Chaisson himself has attempted in a rough and ready way. He's tried to estimate using what at the moment are little more than back-of-the-envelope calculations, but as we'll see, they're quite powerful. He's tried to estimate the amount of energy that flows through a given amount of mass in grams in a given amount of time, in seconds. And he calls this the energy density. This is a measure of energy flows. And here are some of his results. Now, his unit is ergs, flowing through a gram in a given second. But it's the numbers that really matter here. So here are his units. Stars. You do the sum for stars, and you come up with the figure 2. 2 ergs per gram per second are flowing through stars. Now, you do the same calculation for planets, and the figure he comes up with is 75. Note immediately it's a lot more than 2. Now, you do it for animals, and the figure is 20,000. And you do it for human society today, modern human society, and the answer is about 500,000. Now, the point is that even if these calculations are out quite significantly, the differences are so striking that they suggest that there is something to this rough correlation between energy density flows and complexity. So Chaisson's results, if they're accurate, suggest conclusions of fundamental importance for big history. Most of the universe we've seen has remained very, very simple. Imagine someone picks you up, they plonk you randomly somewhere in the universe, completely randomly, and you reach out and you grab a handful of the universe, what are you going to grab? You're not going to grab a person. You're not going to grab a planet or a star. The odds are overwhelmingly that you will grab a piece of cold, empty vacuum. So most of the universe is extremely simple, yet the upper level of complexity has increased. And Chaison's calculations suggest that living organisms are more complex than stars, and modern human societies may be amongst the most complex things we know. This, I think, may be the answer to the student who's depressed by the sense that the scales of the modern accounts of creation, of big history, make them seem small and insignificant. Now, I have to say that Stephen Jay Gould disputed this sort of conclusion in a famous book called Full House, which is full of baseball statistics. But his real objection, I think, was not to the idea that I'm suggesting, but to the idea that the average level of complexity has increased. In fact, as I've said, the universe remains very simple. It's simply that some very complex objects have appeared, and those are the things we're going to be interested in. It's not that the average level of complexity has increased. Now, there's something else we can say about complex things. More complex objects appear to be rarer and more fragile than simpler objects. And that's why, even though they've appeared, they may not have changed the average level of complexity of the universe as a whole. Stars, for example, are more common and survive longer than butterflies. And the simplest thing of all, the vacuum, is of course much more common than either. So if you're complex, you're probably rare, you're probably also fairly fragile, which is an idea that I think has quite a striking message for modern human society, which is fantastically complex. Okay, let me summarize these ideas. Roughly speaking, it seems that complexity can be measured by the density of the energy flows through different complex entities. And these calculations suggest what intuition suggests as well, which is that over time, the highest levels of complexity have increased. More complex things have appeared in the course of the 13 billion years that the universe has existed. Now, it has to be said straight away that a physicist hearing this sort of argument might be worried that there's something paradoxical about them. For at first sight, it seems to contradict one of the most fundamental laws of physics, and that's the second law of thermodynamics. Now, to deal with this argument, I'm going to talk very briefly, remember, as a historian, not a physicist, about the laws of thermodynamics, because we have to get this argument straight. What are the laws of thermodynamics? They describe the relationship between energy and work. Work simply means the ability to make things happen, to cause change. So it's a very fundamental concept in any understanding of the universe and the nature of change. The first law of thermodynamics, and I should say both of them were formulated in the 19th century, says that the total amount of energy available in any closed system, that's any system closed off to other flows of energy, and the universe itself is a closed system, is fixed. The total amount of energy in a closed system is fixed. That's the first law. However, at any particular point in the universe or any particular time, the form, the distribution, and the intensity of energy can vary. And this matters because work can be done only when energy is distributed unevenly. If it's distributed unevenly, it can flow from one place to another, from one level to another, from the top to the bottom of a waterfall, from the boiler to the condenser of a steam engine. So for energy to do work, there have to be inequalities, gradients, differences of some kind. Now, there's one more thing about these flows of energy. As energy flows along these gradients, along these inequalities, its distribution tends to even out. And what this does is reduce the capacity of energy to perform work. Let me just give a very familiar example, the battery. A battery, a charged battery, is charged in the sense that one of its terminals has a surplus of electrons, the other has a deficit of electrons. There's an imbalance of electrons at the two ends of the battery. As the battery does work, electrons flow from one terminal to the other until eventually this distribution of electrons has evened out. And at this point we say the battery has run down. Now note that energy has not disappeared. Nothing contradicts the first law of thermodynamics. Energy is simply distributed more evenly, so it cannot flow or do work. What the physicists say is that the level of simplicity or disorder, and the word they use is entropy, has increased. Entropy has increased. Things are evened out. There's less possibility of energy doing work. The second law of thermodynamics was formulated by a German physicist, Rudolf Clausius, who lived from 1822 to 1888. And what it does is it generalizes these principles and states them in the form of a scientific law. And what it states essentially is that differences in energy levels tend to diminish as work is done, so that entropy, this measure of disorder or simplicity, increases. What this means in layman's terms, I think, is the amount of energy that can do work is steadily diminishing. I think what that means when applied to the universe as a whole. Applied to the universe as a whole, what this seems to mean is that energy flows ought to be decreasing over time. Incidentally, if you doubt that the second law of thermodynamics affects your daily life, think of the bedroom of a teenager. And the question is, does disorder naturally increase? Well, yes. How do you reestablish order? You have to put a fair bit of work into it. So this is a sort of very elementary personal example of what we mean by entropy. Now, one of the consequences of this argument is, as Stuart Kauffman puts it in a book on complexity, as follows. The consequence of the second law is that order, and I've used the word structure or complexity, order, the most unlikely of all possible arrangements, tends to disappear. It follows that the maintenance of order requires that some form of work be done on the system. This, incidentally, explains why you need energy flows to maintain complexity. And he goes on. In the absence of work, order disappears. Hence we come to our current sense that an incoherent collapse of order is the natural state of things. Or to put it in very simple terms, the universe ought to be getting simpler and simpler and simpler, rather than more and more complex. Complexity ought to be decreasing, not increasing. So that's the problem. And it's a problem that scientists are likely to see very quickly in facing this idea of increasing complexity. So how can we deal with it? How can the upper levels of complexity increase if energy flows in the universe are constantly being run down? There have been several attempts to solve this apparent paradox. And once again, I'm describing these in extremely simple terms, but I think nevertheless we can get the gist of it. The Nobel Prize-winning chemist Ilya Prigozhin, whose dates are 1917 to 2003, suggested that there may exist within matter itself a spontaneous tendency towards self-organization. In other words, what he's hinting at is the possibility that there are laws of nature that we don't yet fully understand that tend to counteract the breakdown of order described in the second law of thermodynamics. As yet, though, it has to be said, his ideas are immensely stimulating and immensely rich, but it's been impossible to identify such laws clearly. So this remains a hypothesis to be tested. But there is, fortunately, a much simpler answer to the problem of entropy, and it goes like this. It may well be true that energy differentials are diminishing over the entire universe, so that in some sense, the amount of energy that can do work and create complex things is diminishing. Nevertheless, it may still be true that locally, in little pockets, these differentials, these gradients, are increasing. Let me give you one example which is going to take us into our next few lectures. The force of gravity packs energy and matter into smaller spaces. It's a force that attracts matter and energy together. So it tends to pack stuff into smaller spaces. That itself creates differentials, because it means that there are areas of greater density and areas of lesser density, areas of higher temperature, areas of lower temperature. And eventually we'll see these differences are crucial to the construction of stars. So gravity tends to increase these differentials, and by doing so, it allows local flows of energy. That, incidentally, is why planets are good places for complex beings such as us. Once you've created a star, you have a massive flow of energy, because stars pump energy into the cold of surrounding space. They're like little hotspots dotted throughout the universe. For us, this is very, very important indeed. Gravity, fortunately, has created these powerful energy differentials, and we depend on them. And what it reminds us is that complexity has its own geography. Once complex things appear, like stars, they create the preconditions for more complex things. And that's why when complexity appears, it seems to appear in the universe in little pockets hanging around the first complex stars, the first complex things, which are stars. So complexity, we can say, appears in the hinterland of stars. But it doesn't appear in the stars themselves, or rather higher levels of complexity don't appear in stars. What happens? In stars, the energy flows are too violent. In empty space, well away from stars, the energy flows are too weak. Planets, which hang around stars in their hinterlands, are just right. And we can think of this as the Goldilocks principle. So it's no accident that increases in complexity are likely to occur around stars. So where there are sustained energy flows, for example near stars, but not too violent flows of energy, complexity can build and accumulate over long periods of time. Eric Chaisson has suggested a third possible source of free energy, of energy that can do work, and that's the expansion of the universe itself. He's suggested that the universe, as it expands, constantly creates new energy imbalances, and this ensures that work can always be done somewhere in the universe. But the crucial thing for us is the knowledge that even if the second law affects the universe as a whole, it doesn't necessarily affect every particular corner of the universe. And we live in a corner where there are huge energy flows, where complexity can be created. So, my conclusions about complexity do not contradict the second law, because in the long run, local energy flows do diminish energy differentials in the universe, but while they exist, they can create complex things. So wherever there are local flows of energy, it's possible to create complex things. Now, that's a long and elaborate tour around the second law of thermodynamics, and it's necessary to clear the ground for our understanding about the nature of complexity. The rest of this course will trace the astonishing creative process of increasing complexity as new complex things appear, leading eventually to you and me and modern human societies. The idea of increasing complexity will provide a thematic unity for this course. In the next lecture, we'll ask another unifying question about big history, and that is this: why should we trust the astonishing claims made by modern scientific accounts of the past? What is the status of the story that we can tell within big history? Thank you. In the previous lecture, we discussed one unifying idea in this course. As we've seen, this course covers so much territory that it's very important to be clear about the ways in which we can construct a coherent account across all these disciplines. And the idea we looked at in the last lecture was the idea that to fully understand the past on the scales of big history, we need to explore it at multiple scales. And we saw that each scale can illuminate the others. We also saw that each scale can affect how we understand other scales. For example, I ended with the idea that I said depressed many of my students, and indeed it did, which is that the properties, now the phrase emergent properties I'm using in a slightly technical sense. I mean features that are not present in the components from which they're constructed, but appear only when those components are assembled in specific ways. Now, the idea of emergence is going to be immensely important in this course, so I'm going to take a bit of time to try and clarify it. Here's a very simple illustration. You could study the properties of hydrogen and the properties of oxygen as long as you liked, without being able to predict properties of water, which is what you get when you combine two hydrogen atoms and an oxygen atom in a very specific way. The properties of water are emergent properties. They exist not intrinsically in the components, but because of the way those components are arranged. They arise from a particular arrangement of those atoms. Rearrange them differently, and you may get different properties. The idea of emergence, it turns out, is that colossal scales of big history seem to make humans and human history utterly insignificant. Now, as we'll see in this lecture, that is really not the end of the story. So now what I want to look at is a second unifying idea of big history. Because we face another fundamental difficulty, not just the difficulty of scales, but the problem of coherence. What thematic coherence can you possibly find across all these scales and all these disciplines? If you tell a story that begins with cosmology, includes geology, then biology and human history, isn't it bound to be just a ragbag of completely separate stories? After all, in universities, each of these stories is told in quite separate departments, and most of the time, very little attempt is made to link them, to string them together. Is there anything that all these scales and all these different disciplines share? Well, what I want to argue in this lecture is that there is of the difference between simple and complex things. And that intuitive sense of complexity will take us quite a way. There is an incredibly rich body of mathematical, sociological and biological theory on complexity. And I'm really not going to go too far into the nuances, and we don't really need them. Some fairly basic ideas about complexity will take us a long way for this course. So here is an attempt to pin down some of the properties of complex things. Here's the first thing. Complex things like stars or planets or you and me, consist of diverse components bound into larger structures. And I need to add that those structures are patterned in very precise ways. So that's the first thing. You take a lot of components and you put them together in a particular structure. Now here's a second, slightly less obvious feature of complex things. These structures that bring together diverse components display distinctive, emergent is a central idea. And that idea is the idea of increasing complexity. And we've seen already that the idea of increasing complexity provides a sort of structural framework for this course. It's an idea that's emerging in the writings of a number of scholars who are thinking about the implications of big history, of unified accounts of the past. And what I'll do is that this idea links all the different parts of our story in very powerful ways. Furthermore, I'll argue that it shows how each part of the story can illuminate and deepen our understanding of the others. Just as we saw that understanding different scales can help us understand more familiar scales in new ways. Okay, so our theme is complexity. Let's begin by asking, what do we mean by complexity? What is complexity? Now, we all have an intuitive idea